Schrodinger's equations. So the Schrodinger wave equation was a very important discovery in terms of quantum mechanics. And really what it is, it's just a linear partial differential equation. And this partial differential equation allows you to describe the wave function for any given quantum mechanical system. So it lets you write the wave function in terms of a given particle's position as well as its energy with respect to both space and time. And there are two forms of this equation. There's a time independent Schrodinger wave equation and there's a time dependent Schrodinger wave equation. So we'll be looking at both of those, but before we get to that, there are a few things we need to learn about first. So the first thing we need to know about is something called observables. Okay, so what are observables? Observables are something they're also called dynamical variables. Okay, and the reason they're called that is because they're involved in the dynamics of a particular particle. Okay, so examples for this would be position, velocity, kinetic energy, potential energy, total energy. All these quantities are called observables because they help you define the dynamics of any given particle. Note that psi, the wave function of that particle, or time, they are not observables with respect to some given particle because they do not describe the dynamics of that particle. So yeah, just something to keep in mind. Uh, but these quantities like position, velocity, momentum, and energy, I'll just put an E here. These are all called observables for any given particle. Now, the second thing that we need to know about is is what an operator is. Now, an operator is simply uh, some mathematical operation applied to a function that gives you some sort of an output. So, for example, if say I have some wave function psi of x, right, and I'm applying some operator O cap, right? A cap is generally how you denote these. So this will give me some phi of x, right? So it's similar to how you would have a mathematical function, right? So you would have f of x giving you something in terms of x. So you will take some x as an input and then you would get some other function of x as an output, right? What am I writing? My bad. Okay, there we go. Something as an output. So it's a similar concept, but in this case, instead of taking a variable as an input, this function here, this itself is your input for the operator, and then it gives you some other function as an output. Okay, so that's all when it comes to an operator. This is just what an operator is. Now, there's one other thing we need to talk about when it comes to the Schrodinger wave equation, and that is something called the eigenvalue equation. Now, if you're not familiar with eigenvalues, this might seem like some sort of complicated new term. What are eigenvalues? What is the eigenvalue equation? And this is something that has its roots in linear algebra, and this is very important for a lot of different things, especially in quantum mechanics. So I'd suggest you go look this up. But let's just look at what the eigenvalue equation is and what eigenvalues are for our purposes here. All right. So one thing I should mention here, every observable has some sort of operator associated with it. And we'll see why that's important in just a second after we look at the eigenvalue equation. So the eigenvalue equation in general is some g cap into some psi, okay, giving us some lambda times psi, okay. Now, why is this important? Why is this significant? Okay, so let's just look at this a little bit more carefully, right? So you have g cap here. Should probably change the color. You have g cap here, which is some operator, okay, and then you have psi, which is your wave function. In this case, we're dealing with wave functions because quantum mechanics. But here we call it something called as an eigenfunction. All right, again, I'll get to what this is in just a second. And then lambda here is some constant, but this is what we call our eigenvalue. Okay. And then you'll notice that you have the same psi again here, right? So what is this eigenvalue equation? Like what are we getting out of this expression, right? Essentially what it is when you have some function, right? So in this case it's psi, okay? But you have some function and you're applying some operator to it, which is our g cap here, okay? When you apply this operator to this function, you get the same function back in your result times some constant, right? Which is your lambda, okay? Now this particular constant, so you're just saying that, to sum it up, you're just saying that the effect of this operator on this function is just some scalar times that function, some scalar value, some eigenvalue times that function. So the functions in this particular equation are called your eigenfunctions, and the eigenvalue is nothing but a constant that does the same act on that function as this operator. All right. So if I can sum it up here, eigenvalue acting on some function does the same thing as some operator acting on that function. Okay, so this is what the eigenvalue equation is talking about. Again, like I said, this is a linear algebra concept, and you would probably find it a lot easier to understand if you looked at some sort of graphical representation. So there's, in case you're unaware of this channel, there's a channel called 3 Blue 1 Brown, who has some really good explanation videos, especially when it comes to linear algebra. So I'd suggest you go check that out if you want a better understanding of what this would look like graphically. But for our purposes, what an eigenvalue equation represents is that there is some eigenvalue, some sort of a value that when multiplied into that function, actually should probably mention that. So when this is multiplied into our given function, it does the exact same thing as some operator acting on that function. All right. So this is what the eigenvalue equation is. Now you remember I mentioned that for every observable quantity, so for position, velocity, momentum, and all of that, each of those quantities has some operator associated with it. And this is going to be important to us for finding the Schrodinger equation. So we're going to be finding a few different operators for different quantities, and then we'll be applying the eigenvalue equation, so you'll probably get a better idea of that as well. So let's try and find a few different operators for different quantities. Okay. Now, before we do this, of course, we need to define what the function is, what our psi is. So let's just take it as a general expression. So psi is some constant a times e power minus I into omega t minus kx. Now you're probably asking, oh, what is this? Why are we taking it like this? This is just a general format for psi. And the reason we take this is if you look at the actual graphical interpretation of this, this is nothing but a plane wave, meaning your wave front, when you're talking about it graphically, is flat. So you would have it's a little bit hard to show here, but let's say you had some sort of a 3D wave moving like this, right? So every instance in time in front of this wave would be some sort of a flat wave front. Okay, it's kind of hard to show. If this is confusing to you, completely forget I said anything. Just remember that we're taking this general form for psi. That's all. Okay. Now, just a few things that we can derive from this equation, or just in general for this particular psi. You have a term omega here and you have k here. So omega for a given wave is 2 pi nu, okay? And you can also write, we also know from Planck's law that E is equal to h nu, which means nu is equal to E by h. So substituting that back into this equation, you get omega is equal to 2 pi E by h. And if you've seen the previous video about the Heisenberg's uncertainty principle, you'll know that this right here is a common notation that is used. I'll just write it here. H cross is equal to h by 2 pi. This term crops up a lot in our quantum mechanical equations, so we have a simpler notation here. So replacing that here, you will have omega is equal to E by h cross. Okay, so this is just one expression. We also have an expression for k like this. So k is our wave vector in this particular wave equation. Again, if you don't know what I'm talking about, that is just part of the standard wave equation, so you should probably check that as well. K is equal to 2 pi by lambda, where lambda is equal to h by p, p being your momentum. So substituting that back here, you get 2 pi p by h, yes. And then again, you can substitute h cross here, which gives you k is equal to p by h cross. All right. So now we know our wave function, we've talked about omega and k. So let's do what we said we would do at the beginning, and let's find a few different operators for different quantities. So let's start with an operator for momentum, okay? And I'm going to denote this by p cap. Sorry if my handwriting is a bit messy. There we go. So operator for momentum. How do we find this? So again, if you remember the eigenvalue equation, we are saying that there's some operator that's applied on a function which gives you some quantity, which is your eigenvalue, times that function, right? So when we are trying to derive an operator for momentum, we'll be trying to get the eigenvalue, the value that's multiplied with the function, as momentum, so that the operator on the left hand side would then become your momentum operator. So you'll see how that works in just a second. So again, we're taking our general equation for psi, which is a into e to the power minus omega. Okay, where did I mess up here? So this is where our substitutions come in. For let me just, okay, I'll write it again just so that it's clear. So omega t minus kx. Sorry for referring back a lot. So now we have substitutions for omega and k. So when we substitute those values in there, you get e to the power minus I e by h cross t minus p by h cross x. Okay, now we can take out that h cross. So e to the power minus I by h cross e into t minus p into x. So you have a rewritten formula for your wave function. Now let's try and get momentum in our right hand side, which is where you want your eigenvalue. So let's differentiate the wave function here. So let's partially differentiate with respect to x. So dou by dou x of psi is equal to, let's see, that would be I minus I by h cross into minus p into a into e to the power minus I by h cross, or I can just rewrite this as psi. There's no need to rewrite the whole thing again, just as psi, and then that would give us I p by h cross psi is the partial derivative with respect to x. Now if you're a bit confused as to how I did it, this is just your chain rule. So if you look at the psi function here, psi is basically just written as a into e to the power some u. So when you're partially differentiating with respect to x, it would be partial differential with respect to u first, and then into the partial derivative of u with respect to x. That's all I've done here. So you have your partial derivative of psi with respect to x is equal to I by h cross into p into psi. Now you have your p value here, right? So we're just going to take everything else to the other side so that the only value left on the right hand side is p, because remember, that's what we want. We want the eigenvalue to be only p. So taking this to the other side, you have h cross by I partial derivative with respect to x is equal to p psi. We're almost done here. So just to make it a little bit more, I guess, aesthetically pleasing, what we're going to do is we'll multiply by minus I into I on both sides. H cross by I dou psi by dou x is equal to minus I into I p p into psi. Yeah. So remember, this minus I into I is just 1, right? Because I square is minus 1, minus I into I is just 1. So here you can cancel out I and I, which gives us minus I h cross dou by dou x of psi is equal to p into psi. This is your final eigenvalue equation in terms of momentum being your eigenvalue. Okay, and from this we can say that this operator here, minus I into h cross dou by dou x, this operator is your p cap. This is your momentum operator. So hopefully you got an idea of how you would find the operator for any given quantity. You would just rewrite the equation or apply some operation to the equation so that you will get that particular quantity on your right hand side, and whatever operators are being applied on your left hand side would give you the operator for that given quantity. Sorry if I mix it up a little bit, but hopefully you can kind of get the idea here. I'll do one more. So we'll do an operator for energy as well. And after that, I'll just give you the operators directly. I'm not going to derive the whole thing. You can try deriving it. It shouldn't be that hard for the rest of it. So let's do an operator for energy, and let's write that as E cap. Okay. So for E cap, again, you already have your initial equation from before. Psi is equal to A into e to the power minus I by h cross into E into t minus p into x. Yes. Now, for this, you want this E term to come in your right hand side. You want this as your eigenvalue. So we're going to partially differentiate with respect to t this time so that we can get this E outside. So d by dt of psi is equal to, I think this is minus I by h cross into E. Yes. Which is again multiplied by psi, which is this whole thing. And then we again, we only want E on the right hand side. So let's take h cross by minus I to the other side. Dou by dou t of psi is equal to E psi. And then we'll, again, you're almost done here. We're going to do the same thing that we did before just to make it look a little bit better. You have minus I into I on this side, dou by dou t of psi. And here also you have minus I into I, which is again just 1. And this cancels. So you have I h dou by dou t of psi is equal to E into psi. Again, this is your eigenvalue equation. And from that, we can say that this part alone becomes your energy operator, which we have denoted as E cap. Great. So let's give you, I'll just give you the operators for a few other quantities. So what we just found was the energy operator, which is total energy. We also have, of course, the individual energies. You have kinetic energy and potential energy. So let's look at the operators for those. So operator for kinetic energy. Let's call that some k cap. And this k cap, maybe I should actually derive this. This is probably something that you should probably know the derivation for, because for potential energy, it's very simple. Okay, let's do this. So taking this from our previous equation, we already have the partial derivative with respect to x. We already have an expression for this. So you have IP by h cross into a into e to the power minus I by h cross e into t minus p into x. So I've just taken this from our initial momentum derivation. Now we want kinetic energy here. So kinetic energy is not a quantity that is already there in this equation. So how do you get kinetic energy here? We're going to differentiate this one more time with respect to x partially. So you would get dou 2 psi by dou x2, which is equal to IP by h cross whole square, again into the same thing, which I'm just going to write as psi. And then what can we do here? You have this I square, which you can just write as -1. So dou square psi by dou x2. I should say dou 2 psi, but yeah, minus I. Wait, what am I doing? Sorry, my bad. We are writing I square as -1. So minus p square by h cross square into psi. There we go. Now, what we're going to do here is, let's see. Okay, let's just try and rewrite kinetic energy in terms of momentum first, because we only have momentum as a quantity here. So kinetic energy we know is half mv square, but we need this in terms of momentum. So we know that m times v is momentum. So we can write this as m square v square by 2m, which would give us p square by 2m. Okay, so this gives us an expression for kinetic energy in terms of momentum. So let's just try and reconstruct that here. So we have the p square term. We do not want this minus and h square. So let's take that to the other side. My h cross, my bad. So minus h cross square into dou 2 psi by dou x2 is equal to p square by psi. And then we can just divide by 2m on both sides, which would give us minus h cross square divided by 2m dou 2 psi by dou x2, which is equal to p square by 2m to psi. Okay, that was actually pretty straightforward. So now we have our kinetic energy expression here as we derived earlier over here. And now we can substitute that there. I'll just write it as K, representing kinetic energy. So then you would have minus h square by 2m dou 2 psi by dou x2 is equal to K psi. Again, this is your eigenvalue equation, and this operator here is your kinetic energy operator, minus h squared by 2m into dou 2 by dou x2. This is k cap, or your kinetic energy operator. Now, there's a couple more operators. I know this video is long enough already. The couple more operators are very simple. Operator for potential energy, I'll just write that as V of x, which is V cap. Like I said, this is very simple. I'm not going to derive this, but V cap in any case is just directly V of x itself. Okay, so just something to keep in mind. And one more operator here would be operator for position, or x in our case, We're just taking x to be the position. So operator for position x, which is x cap. And again, it is just x itself. So x cap is equal to x. And one last operator that we have here, which is very important, is our Hamiltonian operator, or H cap. Now, what is this? Where did where did this name come from? To be honest, I actually don't know where the name came from. But what is this operator? Essentially, it is just a different operator for total energy. But we will be using this for the Schrodinger wave equation itself. So what is this H cap exactly? So we know that total energy E is equal to kinetic energy plus potential energy, right? K plus V. Now it would also make sense. So if you had some operator O cap into psi, giving you E psi, right? This is your operator for energy. It also makes sense that you can rewrite this E as some K plus V, correct? So by this, what we get is this operator is an operator for E, yes, but it's just the sum of the kinetic energy operator and the potential energy operator. And that's all that Hamiltonian's operator really is. So Hamiltonian's operator, which is denoted by H cap, is just the sum of the energy, sorry. It is just the sum of the potential energy operator, which is V cap, plus the kinetic energy operator, which is K cap, which is V cap is nothing but V of x, and K cap is minus h cross square by 2m into dou 2 by dou x2. This is your Hamiltonian operator. And that's that. So these are the different operators that we should be having an idea about. Now, why do we need to know these operators? That's where our actual Schrodinger wave equation comes into play. So I'll just keep this quick and try and finish this off. So the Schrodinger wave equation. So how do we get this equation, right? Well, if you go back and look at the different expressions that we've got for our operators, you can actually figure out that you can compare a few of them, you can equate a few of them. And we just talked about the Hamiltonian operator, right? So the Hamiltonian operator is nothing but another operator for our total energy. So H cap is equal to E cap, all right? Now, if you look at the individual eigenvalue equations for each of these operators, you notice that E cap of some psi is equal to E into psi, and H cap of some psi, again being a total energy operator, is again E into psi. So you can actually do a couple of you can actually equate a few things here, which will actually just give you the Schrodinger wave equation. So if I just expand this expression here, minus h cross square, my bad, by 2m into dou 2 by dou x2, which is your kinetic energy operator, plus v of x, which is your potential energy operator. This whole thing applied to psi is equal to E psi. This is your Schrodinger wave equation. That's it. So it is, at its core, it is just an eigenvalue equation. You're just applying this Hamiltonian operator to give you this expression of minus h cross square by 2m into dou 2 by dou x2 plus v of x, the whole thing applied to psi, is equal to E times psi. This is your Schrodinger wave equation when it is time independent, because as you can see here, v of x is a pure function of x alone, right? There's no time involved here. We are not considering time. So this this version of the Schrodinger wave equation does not take into account the passage of time, right? Now, how do we get the time dependent equation? Because this is our time independent equation. So that's actually pretty simple. Again, it will come from these expressions here. All right. What are we going to do exactly? Well, we know that h cap E is equal to E cap. Okay, I'm getting mixed up. I'm very sorry for that. H cap psi is equal to E cap psi. So from this, we can equate the actual operators themselves. So that would give us minus h cross square by 2m dou 2 by dou x2 plus v of x comma t. Remember, because we're taking time into account now, the whole thing applied to psi is equal to I to h cross by into dou by dou t of psi, where this is your total energy operator that we derived initially, and this whole thing is your Hamiltonian operator. And this gives you a time-dependent equation for the Schrodinger wave equation. Note here that v of x comma t is now a function of x and t. So it's a position of, it's a function of position and time. All right. And yeah, that's about it. So you have, so again, it's just an eigenvalue equation at the end of the day, both the time dependent as well as the time independent. So I should probably label this. This is your time dependent equation. So there are further things to be done here. We've just found an equation. Now, the important thing, of course, when you have some sort of an equation like this is, finding a solution to that equation. What does the solution to the Schrodinger wave equation look like? What kind of conditions do we need to take into account? And there's also a relation between the time dependent and time independent equations, because if you look at this, you might have a question, how did I just directly take v of x to be a function of x and t, right? How are these two equations describing the same thing? They are describing the same thing. This time dependent equation actually reduces back to the time independent equation. So we'll probably look at that in the next video, because this video has already gone on for too long. But hopefully you've got an idea of what we're doing here, because a lot of people don't really realize what operators are and what the eigenvalue equation actually is and what it means. So hopefully this gave you a better idea of that.